So in this recording, we're going to move to what we call neutrons and heat generation. And we may have three parts talk about the neutron and heat generation under this one. So let's recap what we got so far. What we got so far is to cover the fundamentals of heat transfer, the different mechanisms. Then we move to the basics equation that we use to do the analysis to calculate the heat transfer quantity of interest, which is Q, Q prime, Q double prime, or Q dot. Then out of that, we have seen that using these formula for complex geometries could be hard or could lead to a system of linear equation that maybe needs some computational capabilities. So to overcome this problem, we were able to do the thermal circuit analysis, and we did introduce the concept of thermal resistance, which is the resistance thermal is simply the temperature difference divided by the heat transfer, which is taken from the Ohm's law, which is the electric resistance is the voltage difference divided by the current. That's from Ohm's law, and we use a similarity to be able to drive this equation. And we did actually introduce thermal resistance for conduction, for convection, for radiation. We skipped that part, right? So we mainly covered the conduction and convection. We did that for plane wall, which means it's Cartesian coordinate. We did that for cylindrical shape, and we did that for spherical shape. And the only weakness or the missing information for the thermal circuit analysis approach is we were assuming always it's a steady state, which is going to be a continuously assumed boundary condition all the time. But we also assume there is no internal heat generation. And if you don't have a heat generation, this means that you can simply use that thermal resistance principle. But with having heat generation involved in the problem, the thermal resistance had to be modified a little bit. Then we have shown that if you have a plate type fuel, cylindrical type fuel, spherical type fuel, we have introduced a different types of thermal resistances that we have to use for the specifically the nuclear fuel. Everything beyond nuclear fuel, like the gas gap, the cladding, the coolant, we go back to the thermal resistance without heat generation. So we all covered that for the last few recordings, and we were able to make a summary table showing all these kind of resistances all the time. Just keep in mind, what is the unit of the resistance? So it is basically degree C divided by what? Delta T could be degree C or Kelvin, doesn't matter, they are the same, it's temperature difference, divided by Q. So how much temperature difference you need to drive certain quantity of power between 2 points, which is presenting the nodes of these temperatures. So keep that in mind. When we go to for the British unit, degree C will be degree Fahrenheit. Remember what is power, right? And usually power is energy per time. So you'll find that actually BTU usually per hour. So you'll find that the unit for the resistance in the British system will be Fahrenheit hour divided by BTU. Just keep that in mind because we didn't mention the units during the analysis before because we were doing more analytical and theoretical analysis with no specific numbers. So that's very important. What else we were able to come out with is a correlation for Q as a function of X or function of R, right? I remember. And usually that Q is function of Q dot, and either it's A times X, right? Or it could be actually A times whatever the other variable is. Could be R, could be whatever. But what is the conclusion here that the total heat generated from a fuel can be simply calculated by multiplying the volumetric heat generation, which has a unit of watt per meter cube, multiplied by the volume of that fuel. Then, if that fuel has a symmetry boundary condition, like a center line, and you have symmetry, you have a coolant this side, you have a coolant this side, that Q dot will generate that value of Q, then the heat will split equally from both sides. And we said when we do the analysis, we're going to only take 1/2 because of that symmetrical boundary condition. Let's assume that you have a fuel, okay, and that contains heat generation, and that fuel has insulated surface at one end. So there is no coolant in this side. That's insulated or isolated or adiabatic. Any one of these words mean that there is no rules for heat to come in or out. That's not allowed. Which mean in this case, if I multiply Q dot times the volume of that fuel, all that heat is not going to split. It's going to go one way to the coolant in this side. So please be careful based on the boundary condition. This is new information I'm sharing here, but this is what we did for all this. It doesn't matter. This is plate type or this is a cylindrical type fuel. So keep in mind where is the heat is going based on the boundary condition that you are getting. So now we know how to do the analysis. So the question is, where is that heat is coming from? Again, we have a fuel pellet. Again, I'm going to simplify that by single fuel pellet. There is a gas gap. Then there is a wall of a cladding. Right? So that's my fuel. This is gas gap. This is clad. Then we have coolant outside. So now we can say that, hey, we know that maximum fuel temperature is the center point. I can present the fuel, then the gas gap, then the cladding, then the coolant. So this is Tmax. Then if you call that 1, 2, 3, this is a temperature here 1, temperature here 2, temperature here 3. Then this is T infinity of the coolant, right? And you know that there is QS going through here. You're going to take that Q dot times the volume of the fuel. There is symmetry. Half of that number will give me QS, right? I'm going to split it equally. That's a QS. That's going to come all the way through that resistance. Then I can calculate the fuel resistance, the gas gap resistance, the clad resistance based on the shape of that thing here, cylindrical shape, right? Or plate type shape, depending on conditions of the problem. So if this is X, that's a plate type. If this is R, we took cylinder. Then you do the analysis and calculate the interfaces temperature and the Q and so on. Now we need to stick into the fuel and see how that fuel actually generates heat, okay? How to get that Q dot out of that fuel here, okay? And remember, we assume always that Q dot is uniform so far, but as we go, you will discover that it's actually local value. So to change from one location to the other. So we have distribution and things like that. So let's, again, recall a few things for those who doesn't have any nuclear engineering background. Okay, what's happening? I have a fuel. That fuel contains, example of a fuel is uranium oxide. That's one of the most used fuel in nuclear. So we have uranium, that's called the fuel. UO2 totally here is called the fuel material. But we know that inside that fuel, uranium, we will have uranium-234, maybe uranium-235, maybe there is uranium-238. A combination of different isotopes of uranium. Which one is very important for us, for us to generate heat? Everyone knows that uranium-235 is the one that we're looking for. Why? Because it is fissionable. And this is where the word fission reaction came from, right? We have actually 3 different terms we use for any material. The material could be fissile, could called fertile, or actually could be fissionable. Then I'm going to explain what is the difference between the 3 terms here. I'm telling you, there are senior nuclear engineering students, sometimes they get confused about the 3 terms. So, but again, there is always a nucleus, which is here, I'm talking about uranium-235, it's my interest. This is the one that's going to give me energy. This is the one that's going to go through a fission reaction, and it will give me energy. So how we do that? Again, let's recall what's the construction of an atom, right? We have nucleus what's inside the nucleus? Inside the nucleus, we have positive particles called protons, and these are positive. And there are neutral particles called neutrons, right? And these are neutral, doesn't have a charge. That's inside the nucleus. Then outside the nucleus, we have the shells that contains electrons, whatever the number is, and these are negative charge particles. So these are electrons. So that's the construction of an atom, right? Now let's look to the nucleus. We know that all these are positive particles, but they are not actually going into repulsive force between them, and they do not actually leave the nucleus, right? So the nucleus is kept stable, but what we call the nuclear force. So this is one of the forces that keep the nucleus integrity and doesn't allow these positive particles to actually repel themselves out. So this is nuclear force that hold these neutral particles, neutrons, and the protons together. Then we have to make kind of excitation for that nucleus to generate energy. So what we do, we bring neutron from outside here. That's a neutron. Then we're going to bring that neutron to hit the nucleus of an element. So assume, again, this is uranium-235. I'm hitting that with neutron outside here. Now, I'm adding extra neutron into the system. Now the nucleus is going to be unstable. They need to go back. It needs to go back to the stability condition, which means that it has to push something out, right? That's again the mother nature thing. So we need to kick something out to be able to go back to the stability, right? So in this case, what's going to happen is when this neutron comes in, then the nucleus becomes unstable. And actually, because it's unstable, it's going to break down into what we call the fission product. It's going to split. That's what meant by fission. And it's going to give me fission product 1, fission product 2. Okay? These fission products are actually unstable. By the way, just to keep that in mind, when you hit the nucleus of uranium-235 with 1 neutron, it becomes unstable. This instability lasts approximately for 10 to the minus 14 seconds before it splits and give me the fission product 1, fission product 2. Okay? Then these fission product 1 and fission product 2 are also unstable. As the nucleus here, after it get hit with neutrons, it's unstable. The nucleus is trying to become stable. It splits, but whatever fission product is coming out, it's also unstable product. Then, within 10 to the minus 17 seconds, these fission products, to be stable, they're gonna emit some of these neutrons out. So that's where we're gonna get neutron out. And sometimes we've got 2 neutrons here. And that's why we said any fission reaction is producing 2 to 3 neutrons out. And this is the only way for these fission product to become stable. So it takes 10 to the minus 17 seconds for this initially unstable fission product to emit neutrons out, trying to become stable. So this will try to bring these fission product into a second phase. Trying to reach the stable condition. Then we discover that in reality, it doesn't still become stable. And by the way, going from that stage to that stage, so 10 to the minus 17 to emit neutrons, then the transformation time here could take about 10 to the minus 13 seconds. I'm trying to give you the sensation of the time for each one of these steps. So now these are not fully unstable, but they are partially unstable. What they're trying to do, they start actually emitting alpha, beta, or gamma particles to reach the final stable condition. So that's still unstable. Now we reach the stable fission product 1 and stable fission product 2. And this process of transformation from unstable or partially unstable to the fully stable one could take 10 to the minus 10 to 10 to the minus 6 seconds. That's the time needed from this stage to this stage. Now we reach what we call the stoppable, or the fission reaction will stop. So to go from here to here, you can actually count how many fraction of seconds that you need to reach the final product. That's the story of a fission reaction. One thing to remember, we usually write, if I have any element, we have two numbers here, right? There is a N number and there is Z number, right? What is N? It's the atomic number. And Z is the mass number, right? Or the atomic mass number. Let's write down atomic mass. So the atomic number is simply the number of protons in the nucleus, while Z is actually the summation of the number of protons plus the number of neutrons in the nucleus. Okay? So Z minus N should give you the number of neutrons inside that nucleus. For example, if you say that uranium, it's 92,235. So that's telling me that I have 92 protons inside that nucleus, and this 235 is actually the proton plus neutron. So the proton is 92. You can get the number of neutrons out of this. Okay, that's how we read that number here. Then there is a very famous chart talk about the stability chart. I'm not going to go into physics here, but this is the plot between the N, right, and Z, number of neutrons, and the atomic mass. And this is very clear. That's a stability zone, that curve like this, right? And we know that this is not linear. If you split any atoms linearly, you should have that straight line 45 degree. But this is the zone of stability. Actually, this line should go through this. The early stage of that line should go through the stability region here. Then it goes out like this. So at very low, smaller number of Z, the ratio of neutron to proton is actually 1:1. Then it goes to, the ratio here is about 1.25 and go all the way here up to 1.52. That's the ratio of the number of neutrons to the number of protons in the atom, to be sure that you are in the stable condition. So let's assume that you have a product here, which means that it's out of the zone of stability. This nucleus need to become stable, so to start actually decaying things. So in this way, it's gonna decay beta, or can actually decay down there to emit neutrons out. So that's neutron emission. That's beta emission. Then gamma can go into this way to tend to go into the more stable condition. Again, that's a basic physics thing, but I'm just reminding you about this information. One more information that you need to know, that fission product and that process of fission depends on the energy level of the neutrons. We have basically two different levels of neutrons. Low level, which we call actually thermal neutrons, and high level. When I say high level or low level, that's high or low level of kinetic energy, how fast these neutrons are. And this is actually called fast neutron. And that's how we classify actually the reactor. These are thermal spectrum reactors, like light water reactors, which means that the level of energy for that neutron that it hits the nucleus for fission reaction is low. When I say low, I mean we're going to talk about this, less than 1 eV, electron volt. When we say high one, it's actually greater than 10 to the fifth eV. So if you have a low level of energy neutron hitting your nucleus, that's a thermal spectrum fission reaction, and that's very common for the light water reactors. If you have a fast level of energy for that neutrons greater than 10 to the fifth electron volt, this is what we call the fast spectrum neutrons, and that's applied for the fast reactors like sodium or lead or things like that. So this is just a short story here about the fission reaction, give you some sensation about the time of each process from the moment of hitting neutron to the nucleus all the way to reach the stable fission product. And what's happening for every time you move from one stage to the other, there is always energy. There is always energy generated for each one of these processes. So that's how we generate energy, by hitting the nuclear fuel with neutron. In reality, in that fuel pellet, we don't have a single nucleus. We have large number of nuclei, right? So there is number of nuclei, and you are hitting this fuel pellet with a large number of neutrons. So we are not just dealing with a single neutron hitting single nucleus. We have large number of nuclei per unit volume, and we have large number of neutrons surrounding here. Also, let's assume that you have 10,000 nuclei of uranium-235 and you have 10,000 of neutrons. What is the probability of that neutron is going to hit a nucleus? He maybe missed it, right? So that's what we call the interaction between neutrons and nucleus. He maybe miss it. He maybe hit it, but it's not get absorbed, so it's not going to be causing fission. It's maybe going to hit and scattered away. And we're going to talk about these type of interactions. So there are three key parameters here: is the neutron, the nucleus of the fissionable material, and the what we call probability of interaction. And we're going to talk about each one of these elements separately here. Let me go back into the definition of these three terms here, just to make it clear. So what's fissile? Fissile, it's a nucleus that can go into fission when actually absorb low-level neutrons. So let me write that definition here. So we are talking about the fissile nucleus. Let me use the black one. So we talk about fissile. This is a nucleus that go fission only when absorbed or hit when hit by thermal neutron. And we define the thermal neutron, that the neutron that has low level of energy, less than 1 eV, right? We call that nucleus is fissile. What's the most common example here? Uranium-235. You hit that with thermal neutron, it's going to go into fission and it's going to split. The second one is called fertile. What's fertile nucleus? This is a nucleus that absorbs neutron, but it doesn't go fission. So this is nucleus hit by neutron. In another word, it's actually absorbed, but does not go fission. But what happened when it absorbed that neutron, it get converted into fissile material. For example, uranium-238, when you add to it neutron, it will becomes plutonium-239. This is a fissile material. This can go into fission, right? But this doesn't go into fission. So it get converted into fissile material. Okay. The last one is fissionable. This is the nucleus. Go fission when hit by neutron of at any energy level. So it's not limited by the thermal. It could be thermal or could be actually what? Fast. So it seems to be that fissionable, it's a big category that contains fissile. So every fissionable nucleus is fissile, but not every fissile nucleus is fissionable. So every fissionable is fissile, but not every fissile is fissionable. Just for simplicity, we used to say fissionable atom, fissionable nucleus, but I want to be sure that you guys get the difference between each one of them clearly. Okay, that's a major difference between fissile. So uranium-235 is fissile, right? And so on. So that's how we define this material here. But again, because we don't deal with fertile in this course, it's usually when we say fissile or fissionable, we consider them the same. But again, fissionable is the big father of the category that include fissile underneath or beneath. Okay, so that's a little bit to give you some idea about the fission reaction and the behavior of different nucleus when they get hit with different level of energy neutrons. So now we have, again, as a summary here, we have neutron that hits a nucleus, right? Example, U-235. Then this will produce unstable fission product, 1 and 2. Then after a few seconds, neutrons will come out, 2 or 3. Then this product will continue to become another fission product, 1 and 2, unstable. Then they're going to emit alpha, beta, gamma, neutrino, whatever it is, other particles to transform from partially unstable to a fully stable product. Okay. So, and we said there is energy with everything. So when I say energy, there is different level of energy here. So we have energy carried by the fission product. We call the energy of the fission product. These neutrons will carry a different type of energy. We call the energy of neutrons. Then we have energy carried by these particles too. So there is energy gamma, there is energy for alpha, there is energy for beta. And there is some small other particles like neutrino and things like that. Yeah, that's also included there. So, but let's look to the category here. So we have energy with the fission product. We have energy with the neutrons. And by the way, these called the newborn neutrons. Sometimes down the process, there is some neutrons come here in some specific cases. So we can actually get neutrons as well. And this we call the delay neutron. Okay. But again, let's look to the major categories here. We have energy of the fission product. We have energy of the neutrons. There is energy for alpha, beta, and gamma. Okay. For example, if I pick uranium-235, you will find that the level of energy for the fission product, it's about roughly 170 EV, electron volt. That's the unit. You can convert electron volt into joule if you want. Then when we look to the energy of neutrons, which basically kinetic energy, you will find this value, it's roughly 5 EV. Then there is energy about 6 for the beta. That's for beta. And there is about 13 EV for the gamma. And there is about 8 or 9 EV for the neutrino nu. Then you add up all of these together, you will find that the total energy coming from a single fission, this is the total energy breakdown of the energy of a single fission reaction. If you add up all of these, you will find that single fission of uranium-235, it's roughly producing 202.76 EV, which usually we simplify that by saying it's approximately 200 EV. Sorry, it's MeV, it's million electron volt. It's MeV all the time. So it's MeV, MeV, MeV. Yeah, EV is very small value. So it's 200 MeV, million electron volt, from a single fission reaction. So this is very important to know how much energy is coming from uranium-235 single fission. Now imagine in a fuel pellet how many uranium-235 nucleus you have, how many neutrons around you have, how many potential fission reaction that would have. If I know how many fission reaction would happen per unit fuel pellet, I will multiply that number of reactions by 200 MeV. I can get the total energy out. And by the way, you can convert MeV. It's equal to 3.2 times 10 to the minus 11 joule. Just in case if you want to get the sensation how much 200 MeV would be actually. So 3.2 10 to the minus 11, that's 200 MeV is equal that number in joule here. So one fission reaction of uranium-235 produced 200 MeV or 3 times 10 to the minus 11 joule. Okay.